In this video, we're going to review the concepts we discuss in our modern physics unit. Modern meaning is essentially happening after the year 1900. So everything that we've learned up to this point in physics has been part of what we call classical mechanics, meaning things that we knew before 1900, which explain 98% of the things that we want to be able to explain using physics. The other 2%, we need a few new concepts and ideas, beginning in the year 1905 with Albert Einstein's explanation of what's called the photoelectric effect. And the photoelectric effect occurs when you shine light on a specific metal, could be sodium, potassium, zinc, for example, and electrons are ejected from it. You can create an electric current with this. This is what your solar cells in a battery-less calculator do, or the solar panels that are on top of the school zone signs. They create a current from light shining on a particular metal, and electrons are ejected from it. Now, the incident light will only cause electrons to be ejected if it's above a certain frequency. And this certain frequency is referred to as the threshold frequency. Now, remember from our waves unit that the energy of light is proportional to frequency. The term photon, we'll kind of define later on, refers to a packet of light or a particle of light. We needed Albert Einstein to explain the photoelectric effect. He explained it in terms of a particle. The work function of a metal, which is given the Greek letter psi, is the minimum energy needed to remove that electron. So it's basically related to the threshold frequency. It's the energy of the minimum packet of light, if you will, that's needed to cause this effect to begin happening. So, for example, suppose you have a certain metal that has a work function of 6 electron volts. An electron volt, remember, is a unit of energy that's really, really small. It's proportional to, or it's equal to 1.6 times 10 to the negative 19 joules. So, if you shine low energy light on this particular piece of metal, say 4 electron volts, nothing happens. If you shine light on there that is 7 electron volts, slightly more energetic, that's above the work function of the metal, and so it's going to eject an electron. A little black dot with a negative sign in there is an electron. The leftover energy, after you subtract 6 volts, goes into the kinetic energy of the electron. It's moving pretty fast. And so 7 electron volt light will eject an electron with an energy of 1 electron volt. If you shine 10 electron volt light on that same piece of metal, it'll eject an electron with 4 electron volts of kinetic energy. So all the leftover energy of the light goes into the kinetic energy of the electron as it moves away. So we can find the kinetic energy of the electron by simply taking the energy of the light, the photons, minus the work function, which in this instance is the 6 electron volts. And so we can write a real simple equation. The energy of an electron is equal to the energy of the photon minus the work function. Again, it's most convenient to do these in energy units of electron volts just because they're smaller. Photons and electrons are very small, and so we measure their energy with a small unit. Now, the photoelectric effect was not very well understood in the year 1905 because everybody was treating light like it was still a wave. Albert Einstein, who was currently working as a patent clerk in those days, won the Nobel Prize by explaining light as a particle. And so what we observe in the photoelectric effect is that increasing the frequency of the light, remember the frequency of the light is proportional to its energy, increases the energy of the electrons, kind of like the example we just looked at. Increasing the intensity or brightness of the light increases the number of electrons. So you don't get faster electrons, you simply get more of them. Now that's the exact opposite of what would happen if light was acting like a wave. And that's why it was very, very confusing back then. So let's kind of draw a couple of examples. Let's suppose that we have dim red light. Remember, red is low energy light. on a metal. So since it's dim, we're going to have a small number of electrons ejected. So I drew 2 photons, which means there'll be 2 electrons ejected. And there's going to be small energies because red light is very low energy. If I increase the number of photons, packets of light, and I make it bright red light, now I'm going to get a large number of electrons, but they're still going to be moving relatively slow. Relatively slow because red light is low energy. If I make it blue light, now the electrons are going to have more energy. Notice that they're going faster. And it'll still be dim blue light, so I'll still get a small number of electrons. So changing the frequency changes the energy of the electrons. Changing the intensity increases the number of electrons. Those are both important facts to remember because they show light acts like a particle rather than a wave. So if we don't ever get to the threshold frequency, then nothing happens. So for instance, if it was infrared light shining on this piece of metal, we wouldn't get any photon or electrons at all, no matter how intense that light was. And again, the definition of a photon is a light particle, sometimes also referred to as a packet of light. Typically, when we're studying the photoelectric effect, it's useful to graph the energy of the electron versus the frequency of light, because that's the easiest thing to adjust. Now remember, the frequency of light is proportional to its energy. Remember, we first have to reach some threshold frequency, call that F subscript 0, and then after that, increasing the frequency will cause the energy of the ejected electrons to increase linearly. So they'll slope up and to the right, kind of like that. The x-intercept would give you the threshold frequency. If you trace that line backwards to the y-intercept, that tells you the work function, like how much energy you would need to shake an electron loose to begin with. The slope of that line is referred to as Planck's constant, which is a super duper important number. For right now, it just tells us about how much energy each photon of light can have. But it's really much more important than that in a broader sense that we won't necessarily get to learn about. So if this was a a graph of lead, and I graph sodium right next to it, sodium has a lower threshold frequency. Therefore, it's got a lower work function. But it's still going to have the exact same slope, because each additional step increase in the frequency of light will cause the same additional step increase in the energy of the light, and therefore the energy of the photon. So any graph that you put on here is always going to have the same slope, which is equal to a number we call Planck's constant. The values for Planck's constant, depending on the units you're using, 4.14 times 10 to the, that should be a negative, 14 electron volt times seconds, or 6.67 times 10 to the negative 34 joule times second. You can see it's a very, 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 very small number. And the size of that number actually determines a lot of the really important properties of the universe. Now we also use the photon model to explain how atoms absorb and emit light. You want to be real fancy, you can call that atomic absorption or emission. So an atom, a specific element, such as helium or neon, neon's a good example, will absorb and emit light only at certain specific frequencies, and they're always the same for a given type of atom. So for instance, street lamps always are yellow because they're always filled with sodium. Sodium glows yellow. And so we have to use, again, the photon model of light to explain why sodium always glows yellow. So absorption occurs, according to this model, when a photon collides with the atom and gives its energy to an electron. It's like the electron absorbs the photon and takes its energy, and the photon no longer exists. Now that's not violating any of our conservation laws. Energy is still being conserved, and photons don't have any mass, so we don't have to worry about mass being destroyed. So it's okay to create and destroy photons. In an emission, an electron loses a bunch of energy by creating a photon. So the photon takes away the extra energy, the electron loses it. So the key thing to understand is that the electrons in an atom can only have certain specific energies. This is what the word quantized or quantum means. They can only have certain specific energies, and they can't have energies in between those two energies. So to kind of draw a real simple example, let's say you shined white light onto neon. Remember, white light is just made up of all the different colors, so I drew assortment of colors in there. All of those will pass through the neon except for that one kind of orangish color, I guess. That kind of orangish color gets absorbed by the neon. If we take another sample of neon and we heat it up, like in a neon sign for instance, it will only emit that particular color. It will emit the exact same color. There may also be a few extra colors that are emitted that we wouldn't necessarily see before. And we'll look at why that is in just a second. So here I drew a violet line in there. So the hot neon gas is glowing at those specific colors. So a neon sign, like a true neon sign, would always glow at the same colors. If I want it to be different, like a red neon sign, then I would use actually a different gas, like argon or helium or something like that. So the way that we understood these things, the device we used, is called an atomic energy level diagram. And what that does is it represents the possible energies that an electron in an atom can have, kind of like rungs on a ladder. So an example might look like this. The higher up we go, the more energy the electron has. So at the very bottom, in this particular example, an electron would have negative 15 electron volts of energy. And the second level would have negative 7 electron volts. The third level will have negative 4 electron volts, and the top level will have negative 2 electron volts. The electron would have zero energy when it's completely removed from the atom itself. Now the reason that those are negatives have to do with the definition of how energy is defined for electric charges. Remember that there's two kinds of charges, and when negative charges go closer to positive charges, they lose energy. Well, if you have zero energy when you're far away from the atom, going closer means you have to have negative energies for the atom. So don't worry too much about the negative signs. What's really important to us is the changes in energy. The bottom level is typically referred to as the ground state. The ground state represents the lowest possible energy that an electron could have, and that's where it prefers to be. Nature prefers low energy states over high energy states. We also can number that by the principal quantum number, n equals 1. The next highest would be n equals 2, then n equals 3, and n equals 4, so on and so forth. You could have a lot more in a given atom. This is just an example. So transitions that are allowed within the atom correspond to quantum jumps between those levels. So if an element is in the ground state, like it is there, then there's only 3 possible transitions. One that's got a transition energy of 8 electron volts, one that's 11 electron volts, and one that's 13 electron volts. It's kind of like climbing a ladder. You can only put your feet where there's a ladder rung. You can't put your feet in between them. And so you can only increase your energy by specific amounts as you go up the ladder. Same thing with the electron. So those transitions are possible because those are where the atom is allowed to exist. So what causes those transitions are photons. Photons of light interact with the atom, and photons that have those exact energies will be absorbed by the atom and cause the electron to gain energy and move up to a higher energy level. So the one that I kind of drew in the pale greenish color, the 8 electron volt, that transition had to have been caused by the absorption of a photon whose energy was exactly 8 electron volts. If it was 9 electron volts, then nothing would have happened. If it was 6 electron volts, then nothing would have happened. So it had to be exactly 8 electron volts to cause the electron to move from negative 15 to negative 7 on our ladder like that. Let's look at some emission. Emission is caused by an excited or high energy electron relaxing or losing energy to the ground state. In the process, it releases energy as a photon. Kind of like something that's moving really fast can lose energy to heat. Electrons can't lose energy to heat, they lose it to photons of light. So kind of redrawing my electron level diagram real quick, same one for before. And let's suppose that an electron is excited to the n equals 4 state. That could be caused by other electrons running into it, it could be caused by heat, or it can be caused by a chemical reaction. So one possible way for that electron to lose energy is to simply emit a 13 electron volt photon. That would cause it to relax all the way to the ground level where it would be stable. However, it could also go down in a series of jumps. For instance, it could release a 2 electron volt photon, followed by a 3 electron volt photon, followed by an 8 electron volt photon. Other possibilities, a 5 electron volt photon, and an 11 electron volt photon. So it can transition downwards via any of those possible paths. It could do a 2 electron volt photon followed by an 11 eV photon. Or it could do a 5 and then an 8. Any of those transitions are possible. So the energies that we'll see from the light that's emitted correspond to those different energy level jumps. 2, 3, 5, 8, 11, and 13 electron volt photons are emitted. So the light coming from that sample would have 6 different colors corresponding to those 6 different energies. Remember, the energy of light determines its frequency. Now the 15 electron volts tells us tells us what the energy is needed to remove the electron, and that's again the work function that we were discussing earlier. So you would need 15 electron volts of energy to completely remove the electron from this atom. The last thing that we discussed was energy mass equivalence. And again, this came from one of Albert Einstein's theory. His equations, while he was working on the theory of relativity, suggested that mass and energy should be interchangeable. In other words, they're 2 forms of the same thing. Another way to kind of state that is that you can convert mass to energy and vice versa. So in chemistry we learned it's impossible to destroy mass. Well, in certain situations you can destroy mass by converting it to energy. This is where the famous equation E equals mc squared comes from. E is energy, m is mass, and c is the speed of light. So just by looking at that, you can see that since c is a big number and it's being squared, that a small m is going to give you a very large E. So you can get a big amount of energy out of a little amount of mass. This occurs during nuclear decay and nuclear reactions. So that's why a nuclear bomb is so powerful, because the mass that's being destroyed multiplied by the speed of light squared is what gives you the energy. There's 2 kinds of nuclear reactions we need to know. The first is a fission reaction. Fission kind of sounds like fissure, which means to split apart. So in a fission reaction, a large nucleus splits into 2 smaller ones. An example would be uranium, which is a very heavy element, splitting into krypton, bromine, and a neutron, free neutron that perpetuates the chain reaction. If you kind of drew a picture, it might look a little bit like that, the relative sizes of those nuclei. The other kind of nuclear reaction is a fusion reaction, where 2 small nuclei combine to form a large nucleus. So an example is 2 hydrogen nuclei smashing together to form helium. Elements that undergo nuclear fission are typically larger than iron. So if you find iron on the periodic table, elements to the right and below iron would typically undergo fission reactions. Elements that are smaller than iron, like helium, hydrogen, carbon, oxygen, would undergo nuclear fusion. So the fusion reaction that I kind of wrote there is what powers the sun. The sun is made of mostly hydrogen. Hydrogen is moving very fast and it fuses together to form helium, and in the process releases a tremendous amount of energy that we feel as sunlight. If we graph the mass per nucleon, it's like the mass per protons and neutrons, versus atomic number, you can see that there's a dip at iron. Iron is the most stable nucleus. So eventually all the matter in the universe should end up as iron. Iron does neither fission nor fusion. So all these processes are continuously occurring. We don't typically notice them because they happen very, very slowly. So things are constantly decaying around us, but we never notice it. So this is the end of our modern physics review. 3 big things we need to know about: photoelectric effect, atomic absorption and emission using the energy level diagrams, and then energy mass equivalence. As always, if you have questions, please let me know and be happy to help you out.